In 1900, Greek sponge divers found a corroded bronze machine at the bottom of the Mediterranean Sea. When scientists finally X-rayed it decades later, they discovered something impossible. Gears. Dozens of precision-cut bronze gears arranged in a mechanism so sophisticated that nothing like it would appear again in human history for 1,400 years. The device could predict eclipses, track planetary movements, and calculate the timing of the ancient Olympic Games. It was built in 87 BCE. We call it the Antikythera mechanism, and it's just the beginning. You're about to see 10 artifacts that shouldn't exist. Not because they're fake, but because they demonstrate knowledge, precision, or capabilities that don't fit anywhere in the accepted timeline of human technological development. These aren't fringe discoveries found by treasure hunters with YouTube channels. They're documented, studied, authenticated objects sitting in museums and research institutions. Objects that make archaeologists uncomfortable because explaining them requires rewriting what we think we know. The Antikythera mechanism sat in the National Archaeological Museum in Athens for decades before anyone understood what they were looking at. The bronze had corroded into an unrecognizable lump. It looked like ancient trash. Then, in 1951, British science historian Derek J. de Sola Price began studying it seriously. What he found would take another 20 years to fully comprehend. The mechanism contains at least 30 bronze gears, though fragments suggest there were probably more. The gears are cut with triangular teeth, a design that reduces wear and tear. The tooth spacing is irregular but intentional, compensating for the elliptical orbit of the moon. Whoever built this understood that lunar motion wasn't perfectly circular. They knew about the metonic cycle, the 19-year period after which lunar phases repeat on the same calendar dates. They incorporated the calippic cycle, a 76-year refinement of the metonic, and they built all of this knowledge into a portable bronze computer you could hold in your hands. Modern reconstructions required advanced machining tools. The ancient version was built with hand tools we barely understand. No previous Greek artifact shows anything approaching this level of mechanical sophistication. And here's what makes archaeologists genuinely uneasy. We have no evidence of the development process, no primitive versions, no earlier attempts. The Antikythera mechanism appears fully formed, as if someone had already spent centuries perfecting the technology before building this particular unit. The standard explanation relies on lost knowledge. Greek astronomy and mathematics were highly advanced, they argue. Archimedes himself reportedly built similar devices, though none survived. The mechanism represents the peak of a technological tradition that was later lost when the Roman Empire shifted focus away from theoretical science. It's a dead-end branch of human innovation, not evidence of anything more mysterious. But the device was found in a shipwreck dated to approximately 70 to 60 BCE, and the mechanism itself was probably built 10 to 20 years earlier. That places it right in the middle of the Hellenistic period, when Greek culture was spreading across the Mediterranean. If this technology existed then, why don't we see it anywhere else? Why no mechanisms in Alexandria, the intellectual capital of the ancient world? Why nothing in Rome, which conquered Greece and looted everything of value? The alternative explanation is uncomfortable. What if the Antikythera mechanism wasn't cutting-edge technology in 87 BCE? What if it was a reconstruction of something older, built by craftsmen who only partially understood what they were copying? That would explain why it appears fully formed. It would explain the absence of developmental artifacts. And it would mean that somewhere further back in time there was a civilization capable of precision manufacturing we can barely replicate today. From the depths of the Mediterranean, we travel to the heart of ancient Egypt, where a wooden bird raises questions that ornithologists and aerodynamics experts still can't fully answer. The Saqqara bird sits in the Egyptian Museum in Cairo, catalogue number 6347. It's carved from sycamore wood, measures about 6 inches long, and was discovered in 1898 during excavations at Saqqara, the necropolis of the ancient Egyptian capital Memphis. It's dated to approximately 200 BCE, placing it in the Ptolemaic period. For decades, it was catalogued as a ceremonial bird figurine. Then, in 1969, Egyptologist Dr. Khalil Messiha examined it more carefully and noticed something strange. The wings aren't shaped like a normal bird's wings. They're aerodynamically designed with a specific airfoil cross-section, thicker at the front and tapering toward the back. The tail isn't a bird tail either, it's a vertical stabilizer. Exactly like the tail fin on an airplane, the weight distribution is precise, balanced in a way that would allow stable flight. Messiha was a scale model airplane enthusiast before becoming an Egyptologist. He recognized the design immediately. When engineers built accurate replicas and tested them in wind tunnels, the results were unexpected. The Saqqara bird generates lift. Not perfectly, the aerodynamics aren't optimized for maximum efficiency, but the basic principles are there. The design works. Add a horizontal stabilizer to the tail, something that might have been present originally but degraded over 2,000 years, and you'd have a functional glider capable of sustained flight. Ancient Egyptians had plenty of bird figurines. They carved ducks, falcons, ibises, all with normal proportions and natural poses. The Saqqara bird is different. The wings are straight, rigid, angled for performance rather than artistic accuracy. The body is streamlined. There's even a notch in the tail section where a horizontal stabilizer could have attached. If this is just a child's toy or a religious symbol, why does it demonstrate principles of aerodynamics that wouldn't be formally understood until the Wright brothers? Mainstream archaeology offers a straightforward answer. It's a weather vane. The vertical tail would catch the wind if mounted on a pole, causing the bird to rotate and point into the breeze. Ancient Egyptians were sophisticated engineers who built pyramids. They understood weight distribution and balance. The aerodynamic shape is coincidental, the result of artistic stylization combined with practical design for a rotating ornament. Reading flight capability into the artifact is overinterpretation driven by modern obsession with ancient astronaut theories. But weather vanes don't need airfoil cross-sections. They don't require precise weight distribution. And they definitely don't need the specific wing dihedral angle, the slight upward tilt that the Saqqara bird possesses. That angle is crucial for lateral stability in flight. It keeps aircraft from rolling uncontrollably. Why would a weather vane incorporate it? Some researchers point to ancient Egyptian texts that mention flying devices. The Thule papyrus, though controversial and possibly a mistranslation, describes fiery discs in the sky. Other hieroglyphs show objects that don't match any known animals or ceremonial items. Could the Saqqara bird be a scale model of something larger? A proof of concept carved by engineers testing aerodynamic principles? Or is it evidence that someone in ancient Egypt understood flight well enough to reduce it to a 6-inch wooden sculpture? The questions multiply when you examine the craftsmanship. The carving is precise. The proportions are consistent. Whoever made this understood three-dimensional form in a way that suggests technical drawing or systematic design process. This wasn't whittled by a bored artisan. It was engineered. We move from Egypt to Iraq to the ruins of ancient Mesopotamia, where a clay jar discovered in 1936 continues to puzzle electrochemists and archaeologists alike. The Baghdad battery isn't actually a single artifact. It's several nearly identical objects found near Baghdad, dated to the Parthian or Sassanid period, somewhere between 250 BCE and 640 CE. Each consists of a clay jar containing a copper cylinder. Inside the copper cylinder sits an iron rod. The cylinder is sealed with asphalt. When German archaeologist Wilhelm König examined them in 1938, he proposed something radical. These weren't storage containers, they were galvanic cells. Ancient batteries, fill the jar with an acidic liquid, vinegar or wine, and you create an electrochemical reaction. The copper and iron act as electrodes. Electrons flow from the iron to the copper through the acidic electrolyte, generating approximately 1 volt of electricity. It's primitive, inefficient, but functional. Modern reconstructions using the same materials and design successfully produce measurable electric current. Here's the problem. There's no evidence that Parthian or Sassanid civilization used electricity for anything. No ancient light bulbs have been found, no electroplating facilities, no wires, no devices that would require electrical power. The batteries exist in complete isolation, unconnected to any broader technological context. It's like finding a USB cable in a medieval castle. The standard explanation suggests they were used for electroplating, coating base metals with thin layers of gold or silver to create decorative objects. Some ancient gilded artifacts show uniform coating that could theoretically result from electroplating, rather than traditional gold leaf application. But this requires assuming a sophisticated understanding of electrochemistry that left no written record, no instructional texts, no evidence of teaching or transmission. Alternative theories propose they were used for religious purposes. Perhaps priests used them to create tingling sensations during rituals, convincing worshippers they were experiencing divine energy. Or maybe they powered now lost devices that we simply haven't found yet. Both explanations require speculation beyond what the evidence supports. What's particularly strange is that the design is optimized. The copper cylinder's dimensions, the iron rod's placement, the asphalt seal, everything maximizes the electrochemical reaction. This isn't a lucky accident. Someone understood what they were building and why each component mattered. They knew that copper and iron in acidic solution would generate electrical current. They knew it 2,000 years before Alessandro Volta invented the first modern battery in 1800. Could this technology have been more widespread than surviving evidence suggests? Organic materials, cloth, wood, leather all decompose. If ancient electrical devices used biodegradable components, we'd never find them. Only the ceramic and metal jars would survive, leaving us with batteries but no appliances to plug them into. From Mesopotamian electricity, we travel to the Andes Mountains of Peru, where stones weighing hundreds of tons were cut and fitted together with precision that modern stonemasons struggle to replicate. Sacsayhuaman sits on a hill overlooking Cusco, Peru. It's a massive fortress complex built from limestone blocks, some weighing over 200 tons. The blocks are cut and fitted together so precisely that you can't slide a knife blade between them. No mortar holds them together, just stone on stone, shaped with such accuracy that the joints are essentially invisible. The complex was built sometime before the Inca Empire rose to power, though exactly when remains debated. The Inca found it already there and incorporated it into their own architecture. The standard timeline attributes construction to the Inca civilization around 1400 CE. But Inca oral tradition recorded by Spanish chroniclers claims they didn't build Sacsayhuaman. They said it was already ancient when their ancestors arrived. They called the original builders a different people, possibly the earlier Quilque culture. Carbon dating of organic material found in the mortar of some sections yields dates around 1100 CE, but that only tells us when those particular stones were placed, not when the original construction began. Here's what makes engineers uncomfortable. The stones aren't just big, they're geometrically complex. Some have 12 angles, fitting perfectly against adjacent blocks that are equally intricate. The surfaces aren't flat, they're slightly curved, three-dimensional puzzles carved from solid limestone. Modern attempts to recreate even small sections using hand tools have failed to achieve comparable precision. The cutting techniques are unknown. The stones show no chisel marks, no evidence of hammering or sawing. The surfaces are smooth, almost polished, with complex curves that would require sophisticated surveying and measurement to achieve. Some researchers have suggested the Inca used harder stones to pound and shape the limestone, gradually wearing it down over months or years. But experiments using this method produce rough surfaces with visible tool marks. The Sacsayhuaman stones don't look anything like that. Then there's the transportation problem. The quarry is miles away. The route includes steep terrain and a river crossing. Moving 200-ton blocks without wheels, without metal tools, without modern machinery requires engineering capabilities that leave no evidence behind. No ramps have been found, no rollers, no rope systems. Just the finished product sitting on a hillside, impossible and undeniable. What if Sacsayhuaman represents the tail end of a much older building tradition? What if the techniques used to construct it were already ancient when the Inca arrived, passed down through generations but gradually degrading as the original knowledge faded? That would explain why Inca construction elsewhere is impressive but noticeably cruder. It would explain the oral traditions of earlier builders. And it would mean that somewhere in pre-Columbian South America, there was a civilization with architectural and engineering capabilities we still can't fully explain. These 4 artifacts, the Antikythera mechanism, the Saqqara bird, the Baghdad battery, and Sacsayhuaman, share a disturbing pattern. They're too sophisticated for their supposed time periods. They appear without clear developmental predecessors, and they exist in isolation, disconnected from the broader technological context of their civilizations. It's as if someone dropped advanced prototypes into the ancient world, then walked away. Human technological development is supposed to be gradual. You invent the wheel, then the cart, then the chariot. You discover copper smelting, then bronze, then iron. Progress builds on itself, each generation standing on the shoulders of the previous one. That's the story we tell, but these artifacts don't fit that narrative. They're anomalies, outliers, objects that force uncomfortable questions about what we think we know. And we're just getting started. What comes next makes these 4 look almost conventional. The Piri Reis map. The year is 1513. You're sitting in a lamp-lit room in Constantinople, the Bosphorus gleaming outside your window. Before you on your work table lies a piece of gazelle skin parchment, and you've just finished drawing something that shouldn't be possible. The coastline of South America curves across the leather in confident lines. The western edge of Africa sits in perfect proportion, and there at the bottom of the world you've drawn the northern coast of Antarctica. The problem? That frozen continent won't be officially discovered for another 307 years. This is the Piri Reis map, and it was found by accident. In 1929, a German theologian named Gustav Adolf Deissmann was cataloguing documents during renovations at Istanbul's Topkapi Palace when he came across a rolled fragment of gazelle skin. The map was dated to the Islamic year 919, equivalent to 1513 CE, and signed by Admiral Piri Reis of the Ottoman Imperial Navy. Piri Reis left detailed notes on the map itself, explaining that he had compiled it from approximately 20 source charts, some of which he claimed dated back to the time of Alexander the Great in the 4th century BCE. He specifically mentioned using a map that had belonged to Christopher Columbus. What made historians pause wasn't the age, it was the accuracy. The map shows the Atlantic Ocean, the coasts of South America and West Africa, and a landmass at the bottom that appears to be Antarctica. But here's where it gets strange. The Antarctic coastline shown on the Piri Reis map matches the subglacial topography of Queen Maud Land, terrain that lies hidden beneath a mile-thick ice sheet. That coastline hasn't been visible for approximately 6,000 years since before the end of the last ice age. In 1960, the United States Air Force became involved. Lieutenant Colonel Harold Ohlmeyer, a cartographer with the Air Force, compared the Piri Reis map to seismic data collected during the 1949 Byrd Antarctic expedition. His conclusion was documented in an official letter. The Antarctic portion of the map, he wrote, showed coastline features that matched the 1949 seismic profile with remarkable accuracy. Ohlmeyer himself stated that the Air Force had no idea how the data on the map could be reconciled with the supposed state of geographical knowledge in 1513. When the Massachusetts Institute of Technology and the U.S. Navy Hydrographic Office conducted their own analysis, they found a correlation coefficient of 0.98 between the Piri Reis Antarctica and modern surveys. That's nearly perfect. The longitude accuracy is equally baffling. The South American coastline is positioned with a precision that European cartographers wouldn't achieve until the 18th century, after the invention of the marine chronometer solved the longitude problem. Yet here it is, drawn in 1513 by an Ottoman admiral who never sailed to South America. Mainstream historians offer a straightforward explanation. The Antarctic portion, they argue, is actually the South American coast, distorted and extended southward. It's a case of mistaken identity, compounded by selective interpretation from believers who ignore errors elsewhere on the map, while highlighting features that seem to match. Piri Reis was simply copying and combining the best Portuguese and Spanish charts available from the early age of exploration. The resemblance to subglacial Antarctica is coincidence, pattern matching where none exists. But the geometry doesn't support this. When the map is properly projected using period-appropriate mathematical techniques, the coastline's orientation doesn't match South America. The river mouths, the mountain ranges, the coastal indentations align not with the continent above it, but with Queen Maud Land beneath its ice. The 1960 Air Force analysis wasn't conducted by fringe theorists or amateur enthusiasts. These were military cartographers with security clearances analysing the map as a technical problem. They had no ideological reason to validate an alternative history. They were simply reporting what the data showed. So where did Piri Reis get his information? His own notes point to ancient sources, charts supposedly from Alexander's time or earlier. Some researchers, including Charles Hapgood, who published maps of the ancient sea kings in 1966, suggest the map was copied from much older source material created by an advanced maritime civilization during the last ice age, when Antarctica's coast was ice-free. Others propose a lost global mapping project, possibly Phoenician or earlier, whose charts survived through ancient libraries like Alexandria before fragmenting into medieval European and Islamic cartography. The questions multiply faster than the answers. How did cartographers achieve modern-level accuracy 3 centuries before the chronometer solved longitude? If the Antarctic coast is misidentified South America, why did US military analysts find it matched Queen Maud Land? And what happened to those 20 source maps Piri Reis claimed to have used? Not one has ever been found. If one map showing an ice-free Antarctica seems impossible, prepare yourself. Because 18 years later, a French mathematician drew a second one. The Oronteus Phineus map, 1531, Paris. You're Oronce Phineus, royal mathematician to King Francis I, professor at the Collège Royal, and you're about to publish a world map that will haunt cartographers for centuries. You've chosen an elegant, heart-shaped projection, a double chordiform that splits the world into 2 lobes. The known continents spread across the parchment in careful detail. But at the bottom of your map, centered on the South Pole, you've drawn an entire continent. Mountains rise from its interior. Rivers flow from highlands to coast. Bays indent the shoreline. You've drawn Antarctica as if the ice weren't there. The map was created by Oronce Phineus, whose Latinized name was Oronteus Phineus. He wasn't a speculative dreamer. He was a serious mathematician who calculated longitude and latitude, designed scientific instruments, and published precise astronomical tables. His map is now housed in the Library of Congress, and it was largely forgotten until Captain Arlington Mallory and researcher Charles Hapgood rediscovered it in the 1960s while studying ancient cartography. What makes the Phineus map impossible is its accuracy. The Antarctic continent is shown at approximately 6,500 miles across. The actual width of Antarctica is 5,500 miles. For a 16th century scholar drawing a theoretical landmass that wouldn't be confirmed for 300 years, that's a remarkable estimate. But the precision goes deeper. The map depicts mountain ranges in roughly the correct position for the Transantarctic Mountains, a massive range that divides the continent into east and west. Those mountains weren't confirmed by expeditions until the 20th century. The map shows rivers flowing from the interior highlands down to the coast. This seemed like pure fantasy until the International Geophysical Year seismic surveys of 1957 and 1958 revealed subglacial river valleys in similar positions beneath the ice. The map includes detailed coastal features, bays and inlets and estuaries that match the bedrock topography mapped by modern seismic reflection techniques. There's even a large indentation on one side that corresponds to the position of the Ross Sea and Ross Ice Shelf. Phineus didn't hide his methods. He was known to use ancient sources, and he worked during a period when Renaissance scholars were rediscovering and translating ancient texts that had been preserved in monasteries and Byzantine archives. The question is what sources he used and where he found them. When Hapgood published his analysis in Maps of the Ancient Sea Kings in 1966, he included testimony from US Air Force cartographers who confirmed that features on the Phineas map matched seismic data from Antarctica. The standard explanation is that Antarctica was a theoretical construct. Ancient Greek scholars like Aristotle theorized about a southern landmass needed to balance the northern continents, a concept called terra australis incognita, the unknown southern land. Medieval and Renaissance cartographers inherited this idea and drew speculative southern continents on their maps. Phineas, according to this view, was simply illustrating an old theory. Any resemblance to the actual Antarctica is coincidental. The mountains and rivers are decorative elements, artistic flourishes, not genuine cartographic data. But Phineas wasn't drawing mythology. He was a mathematician who worked in specific coordinates. When his Antarctic continent is overlaid on a modern map of Antarctica, using the projection mathematics of his era, the fit is disturbing. The interior features aren't random decoration. They correlate with subglacial geography in specific positions. If Phineas was guessing, he made millions of choices about where to place mountains, rivers, and bays. The odds of randomly placing them where they actually exist beneath the ice are astronomically small. Could Phineas have accessed the same ancient source network as Piri Reis? The two cartographers were separated by 18 years and roughly 1,000 miles, yet both produced Antarctic coastlines that match subglacial reality. Some researchers suggest a cache of ancient maps, perhaps from the Library of Alexandria or Byzantine imperial archives, reached Renaissance Europe through Turkish and Italian intermediaries after the fall of Constantinople in 1453. Others propose an even older origin, a pre-Ice Age maritime civilization that mapped the world before Antarctic glaciation accelerated 6,000 years ago. The real mystery isn't just that one mathematician drew Antarctica without ice. It's that multiple cartographers working independently in different countries and different decades all drew versions of the same impossible coastline. Where did they get their information? In 1737, another French geographer would add one more piece to this puzzle, and his map would turn out to be right in a way that wouldn't be confirmed for 220 years. The Philippe Boitsch map, 1737. You stand before the French Royal Academy of Sciences in Paris, ready to present your newest work. You're Philippe Boitsch, premier géographe du roi, the king's own geographer, and the map you're about to unveil will be dismissed as speculation. Your map shows Antarctica not as one landmass, but as two separate islands divided by a sea channel running from one side of the continent to the other. Your colleagues think you're guessing. 221 years later, scientists will drill through 2 miles of ice and discover you were exactly right. Philippe Boitsch was born in 1700 and lived until 1773. He wasn't a fringe figure or an amateur enthusiast. He was a member of the Academy of Sciences and served as the first royal geographer of the French Academy. His map, titled Carte des Terres Australes, shows the Antarctic continent divided by a waterway. It was published and presented to the Academy in 1737, 83 years before Antarctica would be officially discovered by a Russian expedition in 1820. What makes the Boitsch map impossible is precision. It correctly shows Antarctica as two distinct landmasses separated by a channel running roughly from the Weddell Sea on one side to the Ross Sea on the other. This wasn't confirmed until International Geophysical Year. Seismic studies of 1958 revealed that the Trans-Antarctic mountain range divides the continent, and that below the ice sheet, a channel of bedrock sitting below sea level connects the two seas. Modern bedrock elevation maps, including the Comprehensive Bedmap 2 project published in 2013, confirm what Boitsch drew in 1737. West Antarctica is indeed separated from East Antarctica by a below-sea level channel. If you remove the ice, you'd have two islands. Boitsch stated that his map was compiled from various ancient sources and Spanish reports, but he never specified which sources or how he obtained them. He used a stereographic polar projection with surprising accuracy for both longitude and latitude. The map was noted by contemporary scholars but largely ignored as speculation. For the next 2 centuries, geographers assumed Antarctica was a single, solid landmass. It took seismic technology to prove otherwise. The mainstream explanation is that Bourchier made an educated guess based on symmetry principles. If the Arctic had straits and channels and complicated geography, perhaps the Antarctic did too. The prediction was lucky coincidence. He may have been influenced by earlier theoretical maps showing Terra Australis with various speculative features. The divisions shown on his map could reference second-hand reports from French expeditions to the southern oceans that glimpsed icebergs and ice sheets from a distance and made assumptions about what lay beyond. But Bourchier wasn't guessing about generalized features. He drew a specific channel in a specific location, and it matches reality. The probability of randomly placing a dividing waterway exactly where it exists beneath miles of accumulated ice is extraordinarily low. If he was just applying symmetry principles or making aesthetic choices, why does the channel appear where it actually is and not somewhere else? Even more curious, Bourchier claimed ancient sources. In 18th century academic French, this wasn't a vague phrase. It meant genuine old maps, documented historical charts, not modern exploration data. Where did those sources come from? Some researchers suggest Bourchier may have accessed Portuguese or Spanish charts that weren't publicly available, compiled from much older sources held in monastery collections. The Portuguese and Spanish were notoriously secretive about their navigation data, keeping detailed charts classified as state secrets. Could some of those secret charts have derived from Phoenician or Carthaginian mariners who reached Antarctic waters during warmer periods and charted coastlines? Others point to the map as evidence of a sophisticated pre-Ice Age mapping project, with fragments surviving through medieval Arabic and Byzantine archives before reaching European cartographers. The accuracy isn't luck. It's memory preserved through copying and recopying, passed down through civilizations that rose and fell while the ice kept its secrets. From Antarctica's hidden channels, we travel to the opposite pole, where another cartographer drew geography that shouldn't have been possible. Mercator's Arctic map, 1569. Duisburg, Holy Roman Empire. Your Gerardus Mercator, the greatest cartographer of the Renaissance, inventor of the map projection that will bear your name and revolutionize navigation for the next 5 centuries. You're drawing the top of the world, a place no European has successfully reached, and you're depicting something extraordinary. The North Pole isn't covered in ice. It's an open sea surrounding a massive black magnetic mountain. 4 rivers flow outward from the Central Sea, dividing the Arctic into 4 islands. You label the mountain Rupes Nigra, the Black Rock. You've never been there, no one you know has been there, but your sources insist it's real. The map appears as a polar inset on Mercator's famous 1569 world map. It's titled Septentrionalium Terrarum Descriptio, Description of the Northern Lands. Mercator was born in 1512 and died in 1594. He was the official cartographer to Holy Roman Emperor Charles V and the Duke of Cleves. This wasn't a man who trafficked in fantasy. He invented the mathematical projection system still used by GPS systems today. He was a pioneering researcher on magnetic declination and compass variation, doing serious scientific work on how compasses behaved in different locations. Yet his Arctic map shows detailed geography drawn with confidence, depicting islands, channels, and coastal features decades before any European reached the pole. At the centre sits a massive rock formation described in his notes as 33 miles in circumference and the source of magnetic attraction. A giant whirlpool supposedly surrounds it. 4 symmetrical channels flow outward from the Central Sea, creating 4 landmasses arranged in perfect geometric harmony. It echoes ancient cosmological descriptions. The 4 rivers flowing from paradise, the axis mundi at the centre of the world. Mercator explicitly cited his source. He referenced a lost 14th century travel account called Inventio Fortunatae, supposedly written by an English monk describing a voyage to the North Pole. This text was real. Multiple medieval scholars, including the famous John Dee, referenced Inventio Fortunatae in their own work, but every single copy has vanished. Only Mercator's map preserves whatever geography that text describes. The accuracy of the surrounding areas is what makes this truly strange. Greenland, Iceland, and northern Norway are depicted with remarkable precision for 1569. Arctic expeditions of the 17th through 19th centuries found only ice at the pole. But submarine studies in the 20th century confirmed that the Arctic basin bathymetry does include a deep central basin surrounded by submarine ridges, a structure that echoes, however faintly, what Mercator drew. The mainstream explanation is straightforward. The map represents medieval mythology, not geography. The four rivers in Central Mountain are cosmological symbols from religious tradition. The four rivers of Eden, the world mountain connecting heaven and earth. Inventio Fortunatae was likely fictional or grossly exaggerated. Mercator, despite his scientific credentials, was still a man of his time, influenced by medieval legend. When faced with unknown areas on his map, he filled them with speculation and symbolism. The accuracy of the surrounding coasts is overstated. They're recognizable, but distorted. But Mercator didn't trade in mythology elsewhere in his work. He distinguished clearly between reliable data and legend in his other maps and writings. He was engaged in genuine scientific inquiry about magnetic north and compass behavior. Why would he confidently depict Arctic detail, citing a specific source unless that source contained compelling data? And those surrounding coasts, the ones that are supposedly just recognizable but distorted, match modern maps better than they should. It suggests Mercator had access to navigation data from undocumented voyages, expeditions that reached further north than official records admit. Could Inventio Fortunatae have preserved knowledge from earlier Arctic exploration? The Norse reached Iceland, Greenland, and Newfoundland. Their sagas describe voyages beyond documented settlements. Could some of them have pushed further into Arctic waters? Others suggest even earlier Bronze Age maritime cultures may have explored northern regions. Some researchers propose that the ice-free polar sea reflects genuine ancient memory of the Holocene climatic optimum, a warm period from 9,000 to 5,000 years ago, when Arctic ice coverage was significantly reduced. The magnetic mountain might reference genuine navigational landmarks or magnetic anomalies known to ancient mariners. What was in Inventio Fortunatae? And why did all copies vanish? From the Arctic's mysterious geography, we cross to the Pacific, where another impossible map forces us to confront how little we know about ancient exploration. The Yehudi Ibn Map, 1559. You're an Ottoman cartographer named Yehudi Ibn, working in your studio somewhere in the vast Ottoman Empire. You've never sailed the Pacific Ocean. No Ottoman ship has. The empire's naval power is concentrated in the Mediterranean, the Black Sea, the Red Sea. European explorers only crossed the Pacific 37 years ago, and their maps are jealously guarded state secrets. Yet you're drawing the Pacific coastlines right now. The western edge of the Americas from Alaska down through California to Chile, the eastern shores of China and Japan, islands scattered across the vast ocean between. You're drawing them with an accuracy that will take European surveyors 3 more centuries to match. The Yehudi Ibn World Map was created in 1559 and is held in the Topkapi Palace Library in Istanbul, stored alongside the Piri Reis map. It was rediscovered by modern researchers studying Ottoman cartography in the 20th century. What makes it impossible is that it shows the Pacific theatre in remarkable detail at a time when Europeans had barely begun exploring that ocean, and the Ottoman Empire had zero presence in Pacific waters. The Pacific was first crossed by Europeans in 1521 when Magellan's expedition limped across it, losing most of his ships and crew. Balboa had first sighted it from Panama in 1513, just 46 years before this map. Yet the map shows the Pacific coastlines of the Americas and Asia with longitude accuracy that European cartographers wouldn't achieve until James Cook's voyages with Harrison's chronometer in 1768. 209 years later, the map shows California, Baja California, and the Pacific Northwest with detail that doesn't appear in Spanish charts until the Vizcaíno expedition of 1602, 43 years after Ibn drew it. The Alaskan coastline resembles actual Alaskan geography. Alaska wasn't officially explored by Europeans until Vitus Bering's expedition in 1741, 182 years after this map. The coastlines of Japan, China, and Southeast Asia are shown with precision that Europeans struggled to achieve even after decades of trade and exploration. Pacific islands and archipelagos appear in approximately correct positions. There's no documentation of how Ibn acquired this Pacific data. The Ottoman Empire had no Pacific fleet, no exploration program in that ocean, no official presence anywhere near those waters. Ottoman power and influence were focused westward and southward, not eastward across the vast Asian landmass, and certainly not across the Pacific. The mainstream explanation relies on espionage and trade networks. Ibn, they argue, compiled data from Portuguese and Spanish charts that circulated secretly despite official efforts to guard them. Ottoman intelligence networks were sophisticated. They debriefed captured sailors, acquired stolen maps, maintained extensive trade contacts. Fragmentary data from multiple sources could have allowed Ibn to create a composite chart. The accuracy, according to this view, is exaggerated by selective analysis that highlights correct features while ignoring errors. But Portuguese and Spanish Pacific charts from the 1550s were primitive. Even Spanish pilots who'd sailed those routes for decades couldn't accurately chart the coast. Longitude was still an unsolved problem. How did an Ottoman cartographer with no Pacific access produce coastlines that matched modern surveys better than the actual explorers' maps? The longitude accuracy alone is baffling. Solving the longitude problem required Harrison's marine chronometer in 1761, 202 years after Ibn's map. Without accurate longitude, you can't position coastlines correctly relative to each other. Yet Ibn did. Could Ibn have accessed much older charts from a forgotten mapping tradition? Chinese maritime exploration is one possibility. Admiral Zheng has treasure fleet voyages from 1405 to 1433 reached Southeast Asia, India, and East Africa. Some researchers argue they may have reached further. Did Chinese Pacific charts exist, later acquired by the Ottomans through Silk Road trade networks? Polynesian navigators crossed vast Pacific distances for millennia, using sophisticated wayfinding techniques passed down through generations. Could their knowledge have been recorded on charts that filtered to the Old World? Most provocatively, did ancient maritime civilizations map the Pacific millennia before Europeans, with fragments surviving in Ottoman archives? These questions lead us to an act of espionage, because sometimes the most revealing thing about impossible knowledge is when powerful people risk everything to steal it. The Cantino Planisphere, October 1502, Lisbon, Portugal. You're Alberto Cantino, an agent of the Duke of Ferrara, and you're about to commit an act of espionage that could get you executed. You've spent months in the Portuguese court observing, bribing, waiting. Tonight, you finally have it. A secret cartography workshop in the Royal Palace complex has produced a copy of Portugal's most protected secret, a map showing the entire known world, including coastlines that officially haven't been discovered yet. You roll it up as quietly as possible, your heart pounding. If the guards catch you smuggling this out, hidden in cloth, it's over. But what you're carrying will prove something extraordinary. Someone knew this world before Europe claims to have discovered it. The map was commissioned by Alberto Cantino, working as a spy for Duke Ercole d'Este of Ferrara, Italy. It was created by anonymous Portuguese cartographers in 1502. Cantino successfully smuggled it to Italy, and it survived in the Este family collection for centuries. It's now housed in the Biblioteca Estense in Modena, Italy. It's the oldest surviving Portuguese nautical chart showing post-Columbian discoveries, and it's impossibly accurate. The map shows the full Brazilian coastline with detailed features. Brazil was officially discovered by Cabral in 1500, only 2 years before this map was created. Yet the coastline extends thousands of miles with geographic precision, suggesting decades more exploration than actually occurred. The map shows Brazil's coast from approximately 5 degrees north latitude to 35 degrees south. Portuguese records show official exploration had only reached 28 degrees south by 1502. Who mapped the rest? The African coast is shown from the Mediterranean all the way around the Cape of Good Hope and up the east coast with accuracy matching Vasco da Gama's voyage data from 1497 to 1499, but exceeding what was officially published. The Caribbean islands are depicted in detail. The Indian Ocean coastlines, including India and Ceylon, are rendered with remarkable precision for such an early date. The longitude is surprisingly correct for an era without chronometers. The map prominently shows the line of Tordesillas, the boundary established by the 1494 Treaty of Tordesillas, dividing the world between Spain and Portugal. This demonstrates that the map wasn't just geographical but geopolitical, showing territorial claims and strategic information. Italian diplomatic correspondence confirms Cantino's mission to steal Portuguese cartographic secrets. The map cost 12 gold ducats, an enormous sum. Portugal guarded navigation data under penalty of death. Pilots required security clearances. Maps were classified state secrets. The Portuguese crown understood that whoever controlled the maps controlled exploration, trade, and colonial expansion. When King Manuel I learned of the theft, his fury was documented. The question is why? If the map simply showed 2 years of Brazilian coastal surveys, why the extreme reaction? What information on this map was worth killing to protect? The mainstream explanation is straightforward. The map represents cutting-edge European exploration as of 1502, compiled from Portuguese pilot reports, Spanish Caribbean data, and existing Mediterranean Portolan charts. The Brazilian coast shown is consistent with expeditions that occurred but weren't publicly documented immediately. Portuguese exploration from 1497 to 1502 was intensive. The accuracy reflects concentrated effort, not impossible knowledge. The longitude accuracy is overstated, they argue. Projection distortions make modern comparisons misleading. But Portuguese records show only limited coastal voyages by 1502. They hadn't completed surveys of southern Brazil's full coast. Yet the map shows it. The longitude placement of Brazil, Africa, and India is more correct than it should be without chronometers. King Manuel's fury when he learned of the theft suggests the map contained information more valuable than a few years of exploration data. What was on this map that was worth the extreme secrecy? 10 artifacts across 5,000 years. A bronze computer from ancient Greece. A wooden bird designed for flight. Clay jars generating electricity in Mesopotamia, stones cut with precision we can't replicate, maps showing coastlines that shouldn't exist. Each one authenticated, documented, sitting in museums and research institutions. Each one forcing the same uncomfortable question: what if the story we've been told about human history is incomplete? The pattern isn't coincidence. These objects appear fully formed, without developmental predecessors, demonstrating knowledge that arrives too early and vanishes too completely. They're not proof of ancient aliens or lost super-civilizations. They're evidence of something more unsettling. That human capability has risen and fallen multiple times, that knowledge can be lost as easily as it's gained, and that our ancestors may have understood things we're only now rediscovering. The artifacts don't lie, they just refuse to fit the timeline we've built around them.